Okay, now before I leave this very busy page, okay, I just want to talk about our next area. We're now going to talk about vector quantities. And all you have to know about vectors is that they show both magnitude and direction. They will show direction. And these are the quantities we're now going to talk about for the rest of the unit. So without further ado, let's get started. So our first quantity is called position. And the letter we use for position is a D. Notice there's an arrow on the top. So that means it's a vector quantity. It'll have direction. And what you have to realize, another word for position could be thought of as location. And whenever you do location, it's always going to be relative to some origin or zero location. So I want to show you that here with an object below. You have this in your notes, you guys. You don't have to write it down. I just want to walk you through it a little bit. Let's say I want to know where the position of this object happens to be with those measurements. Well, the first thing you have to do is figure out where your origin is going to be. So let's say, for example, I choose my origin as A. So that's my zero location. So this is where I'm going to have my zero. And we're going to be dealing with what we call one-dimensional motion. And in one-dimensional motion, there's only two possible directions you can go in. In this case, it'll be right or left. So what we do with one-dimensional motion is we establish what's called a reference system, a positive and negative direction. I'm going to put that on the side here. And for this question here, I'm going to choose to the right is positive, to the left is negative. Now, if we're measuring from A, like from here, and we go over to where the object is, which is here, can you see this would be the position of the object relative to A. So if the origin is A, then the position, shown as an arrow, would be equal to, can you see it's 35 centimeters to the right of the origin. So it's going to be 35 centimeters, and because it's to the right, it'll be positive 35 centimeters, which can be interpreted as 35 centimeters right of the origin, which is A. But yeah, I didn't have to choose that as my origin. So I'm going to take this away now. Let's do a different choice. Let's choose, for example, the origin as being B. So now B is your zero location. And the position relative to B goes from here to here. Based on B, that's the position. And therefore we can see that according to an origin of B, the position will now be 40 centimeters, but notice it's to the left, which will be negative 40 centimeters, which is 40 centimeters left of this origin. Guys, these are describing the exact same object, but it depends on where you put your origin to figure out its position. Good? So that's position. Okay, let's move on to something that's related to that, and it's called displacement. Displacement has the symbol delta D, which is otherwise known as change in position. Now, it actually has a couple of different definitions that we're going to get comfortable with. The first one is this equation below. That delta D is D final minus D initial. In other words, it's a final position minus your starting position or initial position. And you guys know whenever you have delta, delta will always be final minus initial, as we'll see all the way through the course. Okay, so I'm going to show you guys that later on. But it turns out it has another meaning as well. It is also what we call the start to finish vector, the straight line vector from where you started to where you finished. So I've put a diagram on the right-hand side here of an object that goes along a very interesting pathway. Let's imagine that this object actually started here, then went along that pathway and finished here. Now, the question is, what's the displacement? Well, displacement goes from start to finish. So you draw a straight arrow from start to finish, and that would be called the overall displacement vector. And you know that curvy line that we have there still has meaning. That curvy line would represent gotta learn how to write. Would represent the distance. So the curvy line is the distance. It's how far the object actually moved. Displacement is your straight line vector from start to finish. And it should become clear when you look at this diagram here that distance is always greater than or equal to the magnitude of the displacement. It has to be, because displacement is the shortest possible distance from one location to another because it goes in a straight line. That's good to know. Okay, so you see we actually have two different ideas about displacement. We have this equation, and then we have the idea of going from start to finish. Let's take a look at each as we do the next questions. Okay, so here's the first question we have in our workbook. We have an object starting at a location east of the origin, and then it's going to move and eventually get to 25 meters east of the origin. Okay, let's draw a diagram of this motion first. So we're just going to do a nice long line. And let's say on the right-hand side, that's east, and on the left-hand side, let's call that west. Let's also bring in an origin somewhere. There's your 0 location. And you know this thing actually starts in a location 60 meters east of the origin. Okay, so let's go over here, and there's your 60 meters east of the origin. Now this is where the object actually starts. Not sure what color to use for this. This is where it started. Please understand, it didn't move 60 meters east. It started at this position. Now it's going to start moving. Then it's going to go to a location 40 meters west. So let's put that on here. Here's 40 meters west of the origin. So this object is going to go all the way over to here, like that. And if you want, you can even draw it as an arrow. Kind of goes over to there. Actually, no, I'm going to move that, if you don't mind, down a little bit. So then it goes to 40 meters west of the origin. And then it finally moves to a location 25 meters east of the origin, which is about here. So that same object from here goes back to here. Okay, I'm just going to, bear with me, I'm just going to move this down a little bit. It's a little high for me. There we go. Okay, good. So this is a way we can actually represent the diagram. And our job is to find overall displacement, overall distance. Let's start with displacement. So overall displacement. Turns out there's actually two ways to actually solve this question. The first is to use the equation. So displacement is delta D. Do you guys remember what delta is when you expand it? Always. It is D final minus D initial. But these are vector quantities, and we have to establish a positive and negative direction. So let's do that. On the side here, I'm going to choose east is positive, west is negative. And you can put those onto the diagram. Positive 25, positive 60, negative 40, because that's west of the origin. Now, turns out this becomes a pretty easy question then, because D final, where it finishes, is at positive 25. And D initial is at positive 60. And this gives us an answer of negative 35 meters, or 35 meters to the west. Now, does this make sense? Well, we can actually draw the displacement vector on here. I'll tell you what, before I do, I'm going to need this picture again. So I'm just going to cut this up. Copy that, bring it down. Yeah, I'm going to need that again. Good. Okay, now I'm going to draw it on here. Now remember, displacement goes from where to where. It is your what to what vector. Answer, it is your start to finish vector. So, notice that we started here and we finished here. From start to finish, this is the overall displacement. You can see it's definitely going to the west, and you should be able to calculate that that is actually going to be 35 meters long. Good. So that's displacement. Now let's talk distance. Just going to try to put this into the best location I can. All right. So let's now do overall distance. And you got to remember that distance is a scalar quantity, so you don't have to worry about positive and negatives for this one. You just have to figure out how far this thing actually traveled. We're going to break this into parts. So you can actually, you know what? Now that I think about it, I'm going to move this down a little bit. I'm sorry about that. There we go. All right, so I'm going to break it into sections. The first part of the motion goes from here to here. So how far was that? Well, that would be 60 meters in length. And then the next part of the motion went from here to here. How far is that? Well, that's 40 meters. And again, no negatives, just magnitudes for distance. Then we go back to the origin. How far is that? Well, that would be also 40 meters. And finally, we go to our last location, and this distance would be 25 meters. And honestly, we just had to add those up. So the total distance will simply be equal to 60 plus 40 plus 40 plus 25. And that comes out to be 165 meters. Question is, how many digits should this answer actually have? This is a tough one. We're doing pure addition. That means it's based on precision. And every one of these numbers is precise to the ones, to the one digit, which means this has to be precise to the ones, which it is, which means this is our answer. You do not use significant digits for this question. Good? So that's the distance. All right. Last but not least. So now we have a bike that actually travels 47 kilometers south and then it moves 111 kilometers north. Hey, nice long ride there. And again, we're going to do overall displacement, overall distance. I highly recommend that you guys actually draw this motion first. So realize this time I'm not giving you positions. I'm actually telling you how far it travels. It travels 47 kilometers south. And then from there, it goes 111 kilometers north. Like that. Good. I'm going to reverse the order here. I'm going to do overall distance first, if you don't mind. Let's do distance. Because I'm giving you two distances right here. So this is a pretty straightforward one. So the overall distance, which we call it d total if you want, would be equal to simply 47 plus 111, which is 158 kilometers. Again, it's a scalar, no need for direction. Now, what about displacement overall? Now, this one can be tricky. The first way you can actually do this question is with the idea that displacement is your what-to-what vector. And it goes from start to finish. So, if we draw a vector from start to finish, it started here, finishes up there. So this would represent the overall displacement. And if you're using your logic, you simply have to subtract those two numbers. So 111 minus 47. And that just gives you 64. So you could actually do it just directly with that diagram, that delta D therefore is equal to 64 kilometers north. And done. Just based on the fact that it's a start to finish vector. But there is another method. So here comes method 2. Now method 2 is kind of related to the 47 and 111. We're now going to bring in a reference system. Let's say that north is positive and south is negative. Now, you got to be really careful here. The 47 and 111, they are not positions. So I'm going to make this really clear for you. You cannot use this equation in any obvious way because we don't know positions. So this is gone. What you have to realize is that the 47 and 111, they both represent displacements. So we're actually looking for the overall displacement, delta D total, which is the sum of all the displacements. So it's actually delta D1 plus delta D2. That's what you have to use when you have more than one displacement. And now we use our reference system. Delta D1, you see, is 47 south. That's negative 47. And delta D2 is positive 111, which gives us an answer of positive 64. And you can see that it will be your 64 kilometers north. Okay, this is an excellence level method. You're not required to use it. You could also use just simply start to finish. Okay, well, we finished our lesson. I wish you all the best on the homework. See you in the next lesson.